everyone. Welcome to Quarantalks by the Maths and Physics Club, IIT Bombay. Today, Yashaswini Murthy will be introducing us to differential privacy. Yashaswini graduated from Mechanical Engineering in IIT Bombay in 2019 after being an amazing ISMP mentor to me and is now a PhD student at UIUC. Over to you, Yashaswini.
Right. Hi everyone. Okay, I think Roshni just describes me way she's biased. Don't trust all of her judgments. But yeah, I guess I'll just get started with my talk. Can everyone see my screen?
Yeah, we can see your screen.
Oh, okay. Just a second. Ideally, I'd prefer this talk to be interactive, but unfortunately, this is how it has to be. I don't know how many of you have heard differential privacy, but if you have read the abstract, you know that it deals with protecting individual data, data of people who participate in surveys and stuff like that, just to serve as a motivation towards why we need a notion such as differential privacy. I'm just going to discuss a few scenarios with you. Just a second. So yeah, suppose we have a statistical database that teaches average heights of population subgroups, and suppose further that it is infeasible to learn this information any other way. So basically trying to say that, in other words, height is considered to be a private information. And so then there is private information, and there's something called an auxiliary information, which is hearsay. You just happen to know a few things which are not really captured by the database, or something that is revealed by the database. And so the auxiliary information in this scenario would be that Terry Gross is 2 inches shorter than the average Lithuanian woman. So access to the statistical database teaches Terry Gross's height. In contrast, someone without access to the database, knowing only the auxiliary information, learns much less about Terry Gross's height. Terry Gross's access to the database would give you the absolute value of her height, but if you had no access whatsoever, you just know this relative information. You don't really know much about her height in with specific details. So this brings us to an important observation. So let's say, for example, the statistic is released saying that the average Lithuanian woman's height is so and so and so. So a person who has access to this auxiliary information will immediately be able to deduce what Terry Gross's actual height was. And Terry Gross did not have to be a part of this database, or a member of this database, for this privacy attack on her to occur. So this kind of motivates us to consider a scenario where we're not only trying to protect the privacy of the people who are involved in the database, but also the ones who are not. So in this case, it might seem like a trivial example, because height, you don't feel is that much of a private information in general. But if you're dealing with sensitive attributes such as a person's medical history, or their drug abuse instances, or even their criminal history or something like that, it kind of becomes a pretty important attribute that you have to protect. So this was kind of this was to give you an idea as to how it's not just the people who are in the database who could lose their privacy in participating in that particular survey. So let's consider another scenario. So if you saw the abstract, if you read the abstract, you'd be aware of the de-anonymization of the records published by Netflix. To be precise, Netflix had a competition, an open competition towards people, where people were asked to come up with algorithms to suggest good recommendations based on some ratings given by anonymized users. And a few a professor from Princeton named Narayanan and his colleague basically were able to de-anonymize these records by linking certain data which was anonymized with like publicly available data sets, which in this case happened to be the IMDb database. So they were able to show that even though, like, let's say for example, you have a protected database where you have removed certain fields like a person's name or like their location, and you're just publishing like certain records publicly, and these records might be able to like you might have access to another public database where you could use these public queries to match a particular person, like to like de-anonymize the private records that existed. So these are like in general known as linkage attacks. There are many different kind of attacks, but I'm just like picking out a few here. Also, okay, so these are linkage attacks, and generally you think that if we were to like have a database and we're just releasing the statistics of the database, like some average or like some group, like some average notion statistic, you would think that an individual's privacy would be protected, right? So let's say for example, in the case of genetic data, there are what are known as minor alleles in a person's genome, which kind of determine their phenotypic traits. If a person is susceptible to a particular disease, then they have certain minor alleles in them, and knowing these minor, like having access to these minor allele frequencies which occur in nature, if a person has access to this, like if someone has access to a person's genome, they might be able to deduce what particular diseases this person might already be having or might be susceptible to. And it's illegal to do that, to like take your genome and to like to sequence your genome without your permission and to make decisions based on that. But it still happens. Like insurance companies and then companies which need to like hire you might see if you're like a liability and like basically conduct these kind of privacy attacks. And the worst part is once your genome is out there, it's kind of like it's not something that you can change, because if it's leaked forever. It's kind of there's no way to like alter your genome. If it's your password that you lose out on, you can change your password, but losing out on your genetic data is pretty much like a one-time affair. So one positive, so this is like a small trivia. So I don't know how many of you have heard of the Golden State Killer. So he was the serial killer who was active during late 1970s and early 1980s, and he committed like a lot of crimes, and they were unable to track him for most period of time until very recently. His third cousin uploaded his genetic data, or like underwent a 23andMe profiling, and there was a hit at the FBI as to like they found that this guy's data was like very similar to the data they had on their record, and they were able to like track down the Golden State Killer based on other informations about his like age and everything, and that's how they were able to catch Golden State Killer. In this particular scenario, it turned out to be a positive like consequence of lack of privacy, but ideally you would not want that, and you would not want your cousin releasing like and it was his third cousin, so it's like a pretty far off relationship, but the genetic data in general has such strong correlations between like blood relatives that they were able to identify. So like I cannot state enough like as to how important it is to protect a person's privacy, and just releasing like average statistics of a database does not like it does not like preclude you from losing certain private information. Okay, so moving on to the next slide. Because of these because of like the advent of differential privacy, we see that like a lot of tech bodies have been like incorporating, like a lot of bodies in general have been incorporating this particular notion in order to protect their data. So the informal definition of differential privacy is that it is a system for publicly sharing information about a data set by describing the patterns of groups within the data set while withholding information about individuals in the data set. This is kind of like it's very ambiguous, but like this is what differential privacy intends to serve. Makes it possible for tech companies to collect and share aggregate information about user habits while maintaining the privacy of individual users. So because of the success of differential privacy and the promise of like the theoretical guarantee that it provides, it has been incorporated by several like tech giants such as like Google uses differential privacy in order to like collect data for the surveys, etc. And so has Apple like been actively using differential privacy in terms of like collecting data through Safari and like other entities. And recently US Census US Census Board has also like decided to like use differential privacy in order to protect the individual data. So you can see that the use of differential privacy is like growing with time. And in the 2020 list of top 10 breakthrough technologies, differential privacy was also included as the upcoming technology. And I think the seminal paper for differential privacy was released around 2006. I'm not sure, but it's the brainchild of a Professor Cynthia Dwork, who's a prof at Harvard and also works at Microsoft Research. And ever since she released her paper and also a book, there has been like a rampant research in this particular field where people have extended these notions to like a lot of domains, which I will like get to towards the end. So, how does differential privacy work? What makes it so successful? To like motivate the formal definition, I'm first going to like discuss a particular kind of mechanism which has been used since pretty long time to like collect data. This is known as randomized response. I'm not sure how many of you have heard of randomized response before, but generally in the social sciences, in order to like collect data regarding certain behavior which might be a bit like dicey to reveal, the scientists would ask the people to respond in this fashion. Like they were asked to flip a coin. If they get head, then they answer the truth as to whether they participated in, like, let's say for example, I'm talking about drug abuse. So they're asking a person to answer a survey as to whether they participated in like drug abuse, or so basically just that. And they're asked to flip a coin, and if they get a head, then they answer honestly if it is a yes or a no. And then they flip then if they get a tail, they flip a second coin, and then they're asked to like answer yes or no based on what outcome, like based on the outcome of the second flip. So differential privacy provides privacy by process. What does this mean exactly? We'll get to like the next slide. It actually is just introducing randomness in the data that you will be releasing, the aggregate data that you will be releasing to the public world. So even in this scenario, like if you were able to find out that a person's answer turned out to be yes, you cannot incriminate the person because there is a 1/4 probability that the person will answer yes. So the person can like deny it, saying that there's like a 1/4 probability. I might have gotten just like a tail and a head. So question. Okay. Does anyone have any question? All right, I'll just get back to my talk. So having a yes is not going to incriminate this particular person, and it's important to note that the number of so basically this is like guaranteeing a person's privacy, right? Like you cannot like nobody is going to conclude that you have participated in drug abuse or you're not based on just the response that's going to be there. But you might think that this kind of is going to make your it's kind of going to make the accuracy of your analysis like deteriorated. So how do we test the analysis of such a particular survey? So if you observe this particular process, you'll see that the expected number of yeses is going to be 1/4 times the number of participants who do not have the property P, which in this case can be something like drug abuse, plus 3/4 the number of people who actually have the property P. So I hope that's evident. If anyone has to like wonders why that is the case, then you can just ask me. Okay. So if P happens to be the true fraction of participants having property P, the expected number of yes answers is going to be 1 by 4 times, okay, ignore the 1 there. It should be 1 minus p. 1 by 4 times 1 minus p plus 3 by 4 times p, which kind of comes down to 1 by 4 plus p by 2. So greater the number of samples you have, the greater is your accuracy, which also happens to kind of make sense. And if you equate this particular expression with the fraction of yeses that you get, you will be able to like deduce the percentage of people who have participated in drug abuse. So it's going to not be exact because this is still at the end of the day an expected value, but it's going to be around the accurate value that you were actually searching for, which is a pretty good deal considering that everyone's privacy is like protected and you still have a decent answer regarding your query as to how many people did participate in like drug abuse at some point of time. So this is how randomized response works. So with this definition, we move on to what exactly differential privacy means, or when do we say a particular mechanism is differentially private. So a randomized algorithm M with domain like math BB n raised to the power. Okay, I'll just refer to this as like this is the domain of databases. Like this is how you denote databases. A randomized algorithm M is epsilon delta differentially private. So if for all S which belongs to the range of this mechanism M, and for all X, Y, like X and Y are databases which belong to the space of databases, such that the difference in records of the database is less than 1. We have this inequality satisfied, where the L1 norm of the database X is denoted by like one norm of the database and is defined to be this. And the L1 distance between two databases XY is the one norm of the difference in their like individual records. So to gain an intuitive grasp over this definition is not exactly very easy. Like it took me some time as well. But it's like, if you look at the form of this expression, it's basically trying to say, consider two databases, a database X and a database Y, which are exactly identical except for a single record. And so what you're trying to say is that the query that is being released by these two databases should not be distinct enough for you to like identify this one missing person's information. So the probability that the query could have come from, like the output to the query could have come from database X is bounded by the probability that the answer to the query could have come from the database Y as well. So there's a certain degree of like likeliness that's associated, and closer the degree of likeliness, greater the indistinguishability. So in this case, we refer to epsilon as the privacy budget, because this determines the extent to which you are not able to differentiate this individual person's contribution. So this gives an idea as to how this gives you an idea as to the extent to which a person's privacy is protected, as well as their contribution to the statistic that you're outputting through this query. I hope, and so there's a delta term, which I'll come to. So the last point says if delta is equal to 0, we say M, that should be math M, but okay, M is epsilon differentially private. So what that exactly means is that, so if I have a non-zero delta term there, it means that there is a delta probability that this mechanism fails to be differentially private. There's a delta probability that this is not going to hold. In case we have delta to be in case we have delta to be 0, then what we have is like pure differential privacy, while this technically is an approximate differential privacy definition. So, but yeah, epsilon is generally the one that characterizes your privacy budget, or the extent to which you have like the tightness of your privacy. So lower the epsilon, greater the privacy ensured, because, well, closer are the two adjacent like output distributions. But also lower epsilon entails to like adding greater noise to your mechanism. So it also leads to a loss of accuracy, like by drastic amount. Like it generally always boils down to a trade-off between accuracy and the privacy ensured, which sometimes is like for lower sample sizes tends to be a bit of a problem. Okay, so with definition, we move on to the next slide. So the randomness response that I introduced in the slide before the previous one, that is a ln 3 zero differentially private mechanism, and the proof for that is pretty simple. So you look at the probability that the response is equal to yes given the truth is actually yes, while the response is yes when the truth is actually no. So the ratio of these two terms, the ratio of these two expressions, boils down to 3, which is nothing but exponential of ln 3. And this holds the same, and the same reasoning applies to the case with the answer no. So the ratio, in this case, it's a very simplified version of the definition of differential privacy, but you can see that in this case, the epsilon that you will be obtaining is fixed, and that's going to be ln 3. Until you come up, if you alter the parameter p, instead of let's say a fair head and tail coin flipping, if you have a biased coin, you're going to get a different epsilon based on what the probability of your coin flipping is going to be. So yeah, with this response, we move on to the next most commonly used mechanism to the most commonly used mechanism for differential privacy, and that's the Laplace mechanism. So generally, numeric queries are one of the most fundamental types of database queries. It can be anything. It can be sum, it can be mean, median. You have some database. The database need not necessarily, even if it has categorical values, you can still kind of map them to numbers and eventually boil down to a numeric database. And so these queries map databases to k real numbers. And accuracy of the randomized mechanism output generally depends on the L1 sensitivity of the query function. So now what do I mean by L1 sensitivity of query function? Now consider that the query function is represented by f. This can be you want to output the first k maximum numbers or some statistic which takes a value in Rk. Then the L1 sensitivity of the function is defined as the maximum difference in the queries across two adjacent databases and the one norm of that distance. So you have this will still be a vector in Rk. X and Y are your databases which differ based on one record. So this is basically trying to give you an idea as to how much the maximum extent by which a query function should be changing will change when there is a single record difference in the database, and gives you an idea as to the amount of noise you should be adding in order to hide an individual's contribution to the database. So the L1 sensitivity of a function f captures the magnitude by which a single individual's data can change the function f in the worst case, and therefore intuitively the uncertainty in the response that we must introduce in order to hide the participation of a single individual. So what does the Laplace distribution look like? So a Laplace distribution which is centered at 0 with scale b, we say scale b, which basically means that the variance is 2b squared, is the distribution probability density function denoted by this. The Laplace distribution is a symmetric version of exponential distribution, and the way we define Laplace mechanism is that given a function, a query function of this form, the Laplace mechanism is defined as you input your query, the database, and the privacy budget, and what you output is this f of x plus y1 to yk, where yi are IID random variables drawn from a Laplacian distribution whose parameter is delta f by e. This is the L1 sensitivity of f divided not by epsilon. So this is equivalent to the b expression here. Now this particular mechanism is differentially private, and the proof is in the next slide. So the Laplace mechanism preserves epsilon 0 differential privacy. So the proof is as such. I'll just go through it. X and Y are adjacent databases, two databases such that they differ in one record. And okay, someone's drawing on the screen. Good for you. Such that they differ in one record, and f is some function like a query function, which is basically mapping this database to some vector in RK. So Px basically denotes the probability density function of the mechanism which takes an input as the database X, query function, and epsilon. And Py denotes the probability density for the same mechanism which takes in the input as Y. So for this definition to be satisfied, ideally we take the ratio of like CDFs, like probability, like integral of probability density functions across arbitrary intervals, but not going into like too rigorous theory, which it essentially just boils down to like taking the ratio of the probability density functions on sets whose measures are like not zero. Like if you have sets on like of measure 0, then this expression is not going to really like matter, and we don't really concern ourselves with measure 0 because that's never going to happen. So taking the ratio of the two probability density functions based on the form of the Laplace distribution, which is this, we basically get like a ratio of the probability density. Now if we have k IID random variables, the probability density of that particular random vector is going to basically just boil down into product of their probability densities, and that's just because they happen to be independent and identically distributed. So this boils down to like the product of, well, for IID variables from database X and then for corresponding to Y, and like you just like take like the next step should be obvious, and this step basically follows from triangle inequality, like mod A minus mod B is less than or equal to mod of A minus B. And if you guys remember, like this is basically nothing but the one norm of the query function. And we know that X and Y are adjacent databases, which means that this is essentially equal to delta F, which cancels with the denominator, and we get less than or equal to exponential of epsilon. So, and then the last inequality follows from symmetry, even though that's not really something that we concern ourselves with. So this serves as a proof as to why the Laplace mechanism preserves epsilon 0 differential privacy. And then moving on to, like, there are several other mechanisms apart from Laplace mechanisms which can be used to output differentially private data. But another commonly used mechanism is the Gaussian mechanism. So an alternative to adding Laplacian noise is to add Gaussian noise. And in this case, rather than scaling the noise to L1 sensitivity of the function, we scale it to the L2 sensitivity. L2 is nothing but like the Euclidean norm. So L2, like an L2 sensitivity of a query function is defined in this manner to adjacent databases which still refer in like one record, or like their one norm is differing in one record. And you take the maximum of the query function difference in terms of the two norm. And the Gaussian mechanism with parameter B adds zero mean Gaussian noise with variance B in each of the k coordinates. So if let epsilon, like you can choose epsilon to be arbitrary from 0 to 1. And for a c square, for some number c square which is greater than 2 ln times 1.25 by delta, the Gaussian mechanism with parameter sigma here is used to like refer to standard deviation, greater than c delta to like the L2 sensitivity of function divided by epsilon is epsilon delta differentially private. So I'm not going to go into the proof of this. Just like one observation you need to make is that Laplace mechanism gives you pure differential privacy, as in delta is equal to 0. But in this case, you cannot obtain that. Gaussian mechanism gives you an approximate differential privacy, which means it's a delta probability percent of the time that the mechanism is not differentially private, or it's not outputting a data which is differentially private. Okay. So moving on to the next slide. So another important property of differential privacy is that what is known as the composition theorem. So if I have like one mechanism which is like epsilon 1 differentially private, another one which is epsilon 2 differentially private, and we were to like query both of them together, the data that we obtain is going to be epsilon 1 plus epsilon 2 times differentially private. So so it's the proof is like pretty straightforward. You have like you basically are inputting two adjacent databases to this combination mechanism M12, and which basically just by the nature of its independence with respect to one another, it boils down to this, and you just basically obtain like the last expression. So what does this mean? This has a pretty important significance. So if you have one single database and you were to query it like, let's say, twice, thrice, then the data that you obtain is going to be summation 1 to k epsilon I 0 differentially private, which means the more the number of queries, the greater the loss in privacy, as long as the database stays constant. This kind of makes sense, right? Like, as in, let's say, for example, you have a particular database and you're constantly like querying the same function from the same database. Over a certain number of, once you have a certain number of samples, you can pretty much construct the distribution from which this output has like been obtained, which means you can get a pretty good idea of the underlying database as well, or the actual statistic. So this kind of complies well with our intuition as to how differential privacy should work. So moving on to like one of the last few slides. So what are the properties of differential privacy that makes it so appealing? So it provides you protection against arbitrary risk, moving beyond protection against re-identification. I told you that it's not just linkage attacks. There are a lot of other kind of privacy attacks that can occur on your data, and differential privacy pretty much protects you against all of these. Automatic neutralization of linkage attacks, including all those attempted with all past, present, and future data sets, and all other forms and sources of auxiliary information. So prior to differential privacy, most of the like existing privacy inducing methods tended to be ad hoc, and they also needed to model the underlying database and the auxiliary information that was available. Differential privacy promises like privacy irrespective of the underlying database distribution, as well as the auxiliary information. Irrespective of what auxiliary information is is in your hands, you can still rest assured that the information is still going to be private and nobody's going to glean anything from it. And that's what basically the second point states. And like it's pretty important, I feel. Like if you like look back at the definitions that we went over, we saw that nowhere did we make any assumption over the underlying auxiliary data or the underlying data distribution. So that is a pretty robust formulation in terms of like providing privacy. So another really good property of differential privacy is that you're able to like quantify the privacy loss. So I told you that epsilon refers to as the privacy budget. If epsilon is equal to 0, then there is like absolutely no privacy lost at all. Like the individual contribution is like of no significance whatsoever, because then the two ratios of the probability density distributions turns out to be 1, which means that they're essentially the same. So this epsilon is used to denote your privacy loss, and this permits comparisons among different techniques for a fixed bound on privacy loss, which techniques provide better accuracy and vice versa. So this is also a very handy tool in terms of analyzing how good your mechanism is in terms of like protecting your data as well as providing the accuracy that you want. And it also has a compositional property that we discussed in the previous slide. And there's another really important property of differential privacy, and that is its immunity to post-processing. Once you have obtained a particular statistic from a differentially private algorithm, no form of post-processing is going to like diminish the privacy of the obtained data. You cannot subject it to another randomized algorithm or perform any sort of operations on it, irrespective of the it assumes no constraint on computational power. You can have arbitrary computational power. No matter what resources you have at your disposal, no amount of post-processing is going to yield an output which is going to be devoid of the privacy that was initially promised. So the proof for this is pretty simple. Like, even though it holds for like randomized pre-processing as well, I'll just go over the deterministic case. So let's say, for example, R represents your differentially private output, and there's some deterministic function f acting on this R, which yields R prime. And so we check if this particular R prime has a diminished privacy or something, or basically yielding an epsilon which is greater than the previous epsilon. So probability that f of m of x belongs, like, so R is basically m of x, right? So that's basically just the first expression here. F of m of x belongs to the data set S is equal to m of x belonging to the data set T. This is just like mapping between functions, and this is less than or equal to exponential of e power epsilon times probability of m of y belonging to the data set T plus delta. And this is still going to just boil down to f of m of y belonging to S, because that's how, like, it's just a property of functions. You can think of it as in terms of mapping and stuff. It's pretty straightforward, and which is basically just satisfying the differential privacy property that we were talking about. So even after post-processing, you see that the function has the same privacy budget as the original randomized mechanism. So a data analyst without additional knowledge about the private database cannot compute a function of the output of a differentially private algorithm M and make it less differentially private, no matter what auxiliary information is available. So this is another reason why differential privacy has gained a lot of traction lately and has gathered a lot of proponents for itself. So apart from this, there are, like, even though differential privacy was just intended for the purpose of collecting data for surveys, it has found like wide applications across a lot of domains. Like these are just a few papers that I've come across over the past few like weeks, but I'm pretty sure there's a lot more theory and a lot more papers out there on like different applications. Some of them are like in practice, while some of them are just proposed ideas. So like in order to collect data for like giving you recommendations on different sites, differential privacy is once again employed. To release genetic data statistics, I think differential privacy is very promising. Also data markets, in terms of like like general data markets as well, they also use differential privacy in order to collect and release stats. So power signals from a particular house can lead to a significant privacy leakage, like based on whether you're using based on what like the activity in your like power consumption, a person can glean as to whether you are in your home or not in your home, and can like basically get you to be in a lot of trouble. So if you were to have electric vehicles, based on how you're charging, the person might get an idea as to whether you're like going on a like whether you're at home or you may not be at home, etc., stuff like those. So in order to like protect that data as well, the signals in order to like charge electric vehicles are also released in like a differentially private manner. Then there's differentially private signal filtering, and then location tracking for like traffic information, which is also like your location is also a private data for you. So even that is like released using can be released using differential privacy. And there are like a lot more wide range of applications, and these are just a few that I listed. So you can see how handy this particular technology is. That's it. I think I'd like to conclude my talk.
So thanks, Yashaswini. We have a few questions here.
Yeah.
So someone's asking, who are the yeah, sorry, I had a bit of an internet connectivity issue. Yeah, I lost the previous questions, so I'm just asking one of my conveners to read it out.
Okay.
Yeah, so Drishti will be reading out the questions.
The first question is, who are the pioneers of or in differential privacy currently, and what are the organizations?
Okay, so it was the brainchild of a professor named Cynthia Dwork. I can type it on chat if for everyone to see. She devised it, I think, around 2006 in her seminal paper on differential privacy. And after her, there have been a lot of people who have been pretty active in this field. So she is from Harvard and Microsoft Research. Apart from her, there is a professor at Berkeley called Moritz Hart, who also works in differential privacy. And there's Aaron Roth, who has co-authored a book with her, which is called The Algorithmic Foundations of Differential Privacy, which is pretty much like most of the meat of my presentation is from that book. And it's not, I wouldn't say it's a very easy read, but it gets easier with time. So Aaron Roth from UPenn. Apart from these, there are quite a lot of authors, but these are kind of like the front runners in the field. If you want more information, then I can like speak later depending on what aspect of differential privacy. I think even Jerome, I'm not very sure of the name, is also pretty good. And there is John Ducci from Stanford as well, who worked in differential privacy quite a bit. So these are like the front runners in terms of differential privacy.
So the next question is, when you talk about randomized algorithm, what is your criterion for randomness?
So you saw that, so the criteria for randomness basically just comes up from the probability of the coin flip. So I was telling you that we got the 3/4 divided by 1/4 only assuming that these coin flips are fair, right? Like there's a 50% chance that you get either a head or a tail. But if you were to like make it biased, like let's say 70% head and 30% tail, your epsilon is like going to change. The privacy budget that you're going to have is going to change. And similarly, like the accuracy is still pretty much going to be unaffected, but then the privacy with which you can play is going to change. So that is how I say that the randomness is creeping in. It's basically from the randomness of the coin flip that you're having.
The next question is, the Gaussian noise has a limit depending upon its standard deviation. Does the Laplace noise have any such disadvantages or limitations?
So you can see that, so the standard deviation is pretty much also a function of your approximate differential privacy, right? So your Laplace distribution, if you see, is a function of only one parameter, that is like the sensitivity of the function divided by epsilon. You cannot have epsilon as 0, because if you have epsilon as 0, then this like variance parameter is going to like explode to infinity. And if you were to have like the lower the epsilon, greater the variance in terms of the distribution. So if you have like a greater variance, you can think of you losing accuracy in terms of your data, because the noise that you're adding could have been sampled from like really far off across like from the tails with like a pretty high probability as well. So that is how you kind of like reach limitations in terms of your Laplacian distribution. But Gaussian is like a different aspect, like a different form completely, because it also deals with like this approximate nature of differential privacy, which means that depending on the tail, the standard deviation, there's like a delta probability that your mechanism fails to satisfy differential privacy. So that's like the fundamental differences sort of in terms of limitations when it comes to Laplace and Gaussian.
The next question is, do database languages SQL come in handy, or is it all math?
So the thing is, I told you that we don't really make any assumptions over the database, right? Like we don't concern ourselves with like the underlying distribution at all. The results that you're trying to prove should hold in all generality. So the actual theory is just math. It's just statistics and applied math. But I guess implementation wise, you can like implementation is always different. You can use Python or stuff like that. But no, I don't think SQL really matters.
The next question says this is more efficient when we've got considerably huge data sets since it will give accurate results. Are there any applications of differential privacy given that we have comparatively smaller data sets?
So, well, there are cons to every method, right? Like, this is a pretty valid point. Like, if you have a much smaller database, you kind of like think of it in terms of an intuitive sense. If you have a smaller database, like say a database of 5 people, and you have like a 6th person contributing, automatically the 6th person's contribution is going to be pretty heavy. And if you're trying to hide the 6th person's contribution, you have to pretty much noise to the extent that your accuracy gets compromised. It's in nature of differential privacy to perform poorly when you have like smaller like data sets. But this is intended for like big data. So in that case, like it generally doesn't really matter, because in that case the promises are satisfied. And like just in terms of utility, I think with like smaller databases, you're generally not that concerned with releasing what do you say, like data statistics, because it's like for example, when I was discussing the genetic data and then even releasing minor allele frequencies, which are like existing in very few people, it has to incur a lot of noise, which is still like an area of research right now, and as to how you can kind of enhance privacy for smaller data sets. But as of now, it's still like I feel like it's a intuitive roadblock. You cannot overcome that, at least as of now, until they come up with like a different sort of a formulation which kind of like tends to like smaller data sets. I don't see how you can use differential privacy to like get more accurate results for the same degree of privacy when it comes to smaller data sets. But good question though.
The last question asks for references for differentially private signal filtering.
Sure, I can send some paper to Roshni and she can send to you, and she can send it to you.
Yeah, sure. So I guess yeah, sure. I'll pass on the paper. So I think that brings us to the end of this talk. So I'd like to thank Yashaswini for agreeing to give this talk. It's been a pleasure to have her. And I'd also like to thank the audience for coming and being such a great audience, and hope to see you in future Quarantalks as well.
I hope you guys understood what I said. I had a lot of fun. All the best. I think I'll take off.